Imagine a pristine, six-figure luxury electric vehicle. Now, launch it at 40 miles per hour into a reinforced concrete wall. In a fraction of a second, the front end crumples on impact. That single test destroys hundreds of thousands of dollars in hardware and labor. If you want to know what happens if you increase the speed by just 2 miles per hour, you have to build and destroy another incredibly expensive prototype. That is why physical testing alone simply cannot scale. Before computers, engineers relied on hand calculations, but those formulas have limits. They work for simple beams or blocks, but they struggle to predict what happens to complex parts with holes, curves, and non-uniform materials. Because it was impossible to calculate exactly where the stress would peak, engineers used large safety factors. They were forced to overbuild structures just to guarantee they wouldn't collapse. This led to heavy, inefficient designs. When you overbuild a part, you waste material, increase costs, and in the case of vehicles, consume significantly more energy just to move the extra weight. Finite Element Analysis, or FEA, changed that. It allows engineers to crash digital math instead of physical metal, changing the way we build the modern world. In the real world, a physical object is continuous. It is made up of an infinite number of points. Trying to calculate how every single atom reacts to a force results in calculus problems that are often impossible to solve. To solve the unsolvable, engineers use a process called discretization. We take that complex, continuous shape and break it down into thousands of small, simple geometric pieces called elements. These elements are connected to one another at specific points called nodes. While an individual element is just a simple shape, the computer treats them as an interlocked network. Because they share nodes, a force applied to one point transfers to its neighbors, simulating how stress travels through the entire structure. By breaking an infinite physical object into a finite digital mesh, the computer can finally translate the problem into a massive system of solvable algebra. Once the mesh is built, we have to tell the software how the object exists in reality by applying boundary conditions. We define the supports, the points where the part is bolted down or held fixed, and the loads, which are the physical forces like wind, gravity, or impact pressure pushing against it. Then the solver takes over. At every single node in the mesh, the computer calculates the fundamental spring equation, force equals stiffness times displacement. Instead of one impossible calculus problem, the software builds a massive matrix to solve millions of these linear equations simultaneously. This translation from continuous calculus to discrete algebra allows the software to calculate the resulting displacement of every individual node under pressure. In the post-processing stage, the computer translates those millions of calculated data points back into a physical map that an engineer can actually use. This creates a visual heat map. Red zones reveal stress hotspots where material might fail, while blue zones show areas doing almost no work. This allows for lightweight optimization. Engineers safely remove material from these blue zones, making the part lighter without sacrificing strength. This has a massive real-world impact for electric vehicles. Using FEA to shave off every unnecessary gram of weight is what allows for greater battery range and efficiency. Engineers also use FEA as a forensic tool. When massive machinery fails, like a crane at the Bonneville Dam, simulations can look inside the metal to find the hidden defects and stress concentrations that caused the break. This ability to visualize invisible forces is how engineers find and fix potential failures before they ever happen in the physical world. FEA is the bridge between an engineering concept and a safe, functional reality. From towering bridges to the rockets that carry us into space, every modern marvel relies on these millions of equations being solved before the first bolt is ever turned. Modern engineering is defined by achieving this level of confidence in a virtual environment before the very first piece of metal is ever cast.